What is the purpose of studying a unit, the greatest invention of science? For a very long time, humans have been trying to count and calculate the size or amount of objects. They were curious to know how tall they grew, to count leftover days until birthdays, and to find bigger cake pieces. Unfortunately, in the day of abundance material wealth, people have lost an interest in calculating or measuring size or amount of these objects. Doctors try to understand patients' information and health conditions through various quantitative measurements, such as height, weight, chest size, blood pressure, body temperature, and more. If someone weighs more than his or her height, the person will be diagnosed with obesity. If the body temperature is too high, then the body will be vulnerable to germs, increasing the risk of catching a cold. Measurement is essential when cooking a delicious food. A recipe says how much and what kind of seasoning needs to be added. If it is not properly followed, the food would not be as delicious as it should be. For example, adding a ladleful of salt instead of spoonful can make the food too salty. How people measured objects before measuring tools such as scales, rulers, or measuring cups. It's likely that human body parts were first used as the closet measurement available. Measurements are often unnoticed as they are very well blended in much of daily lives. However, people are surrounded by a countless number of units, including a second, meter, and kilogram. The oldest unit in record is a cubit. Cubit is a length from an elbow to the end of a middle finger when bending an arm, where 1 cubit is about 48.5 centimeters. In ancient Egypt, however, a unit called royal cubit was used. The length from the pharaoh's elbow to the tip of his middle finger plus a width of palm was the standard. This length was used to build a pyramid. The square base of pyramids in Egypt was extremely accurate, as their maximum deviation was only 20 centimeters. Cubit was a very important unit in the West, from ancient Egypt even to modern times. Yard, a unit made in the UK, is no different than a cubit. Although the origin is unclear, some say that in the 12th century, Henry I, King of England, defined a yard as the distance from his nose to the thumb of his outstretched arm, a foot as the length of his foot, and an inch as the length of his first segment of the thumb. In the metric system, 1 foot is about 30.48 centimeters, and 1 inch is about 2.54 centimeters. History tells an interesting tale behind feet as a unit. Napoleon, the Emperor of France, was very short. According to the record, he was 5 feet and 2 inches tall, which is around 157.4 centimeters. But around that time, France and UK were using a slightly different measurement system. In France, 1 feet was about 32.38 centimeters, and 1 inch was about 2.7 centimeters. So in centimeters, Napoleon's was about 167.8 centimeters tall. Since the average height of the French men was 164 centimeters in the 18th century, it is hard to say that he was small. In other words, the length of a foot varied from 25 to 34 centimeters, depending on the size of the feet in many different countries. In the U.S., 1 foot equals 30.48 centimeters since 1959. Human body parts were used as standards and tools for measurement, such as the amount that can be held in 2 hands, the length that can be measured with 2 arms spread out, and the weights that one person can lift up. However, tools in nature were also used as measurements. A branch was used to measure the length, and stones in the same size was used to compare the weight. Eastern countries used body parts as units, too. Chuck, similar to feet, was first developed in China, and chun were all units of length made by the standard of human body. Chuck is a length between thumb and middle finger of an outstretched hand. In Yin Dynasty, 1 chuck was about 18 centimeters. But, the length of 1 chuck gradually increased over time for the leadership to collect more taxes. In Romance of the Three Kingdoms, a Chinese classical novel, Guan Yu, a general in Yi Dynasty, is depicted as 9 chuck tall. 1 chuck is known to be about 23 centimeters. When calculating his height in accordance with the standard today, his height is almost 2 meters 7 centimeters. King Sejong of the Joseon dynasty reorganized and made own measurement called wang, zhuang, chuck. Baekhyun, a Korean musician during the Joseon dynasty, selected medium-sized millets, a type of grain, and put 100 of them in a row and defined the length as 1 chuck, which is about 34.49 centimeters long. 1/10 of Wangzhong chuck was defined as 1 chon. 1/10 of 1 chon was 1 boon and 1/10 of 1 boon was 1 li. In order to measure a long distance, other units were also made, such as 1 chon, 1 chuck, and 1 jang were equal to 10 boon, 10 chon, and 10 chuck, respectively. The ancient Chinese created a new standard to determine the length in the more scientific way than using body parts. As a result, the length was now based on the size of a single grain, which could be expanded to calculate volume and weight. These traditional units became the foundation of many units used today, including meter, a unit of length, and kilogram, a unit of weight. The development of science and technology required more sophisticated measurement system to show precise and detailed differences and to display measurements from many other fields. For example, minute lengths of the boards of semiconductors and the frame size of parts used in cell phones are measured in the unit of micrometers. The degree of hardness, temperature, viscosity, pressure, and more are also measured with units suitable for these purposes. Anyhow, a unit is the greatest invention of the science of all time. When faced with an unknown object, it is in our instinct to begin measuring the object. The purpose of studying this topic is to learn the process in which the standard of measurement used in people's lives are created and to learn the ways of measuring accurately. The other reason of studying measurement is to gauge things that cannot be actually compared directly. For instance, cotton and iron can have the same size but will have different weights. Putting cotton on the left hand while putting iron on the right hand can tell us that iron is heavier. However, comparing and measuring weights with hands are not accurate. Likewise, the exact length cannot be measured simply by looking at it. Thus, it is necessary to study the kinds of tools that allow people to accurately compare size and quantity. If we understand what practical measurement is, we will realize the importance of measurement in our lives. Why is measurement the foundation of a nation? Since the beginning of the civilization, coming up with measurement system to calculate an object's size, length, weight, and volume was essential. Unification of measurement system was also critical to facilitate individual trades and to effectively govern a nation. For example, yard-pound system used in the U.S. caused the spacecraft accident. At the end of the 20th century, the U.S. spacecraft on the mission to Mars to explore its climate crashed because of atmospheric friction while approaching the orbit of Mars. The cause of the accident was error in calculation, whereas Lockheed Martin, the manufacturer of the spacecraft, used pound as a unit of weight. The National Aeronautics and Space Administration calculated momentum with kilogram. It is unbelievable that NASA could make such catastrophic mistake. A $125 million project came to nothing in a moment due to a simple miscalculation between meter and pound. This teaches us a very important lesson on the need for standardizing the measurement system across the globe. Meter and kilogram are the most frequently used units. The term meter is derived from metron in Greek or metrum in Latin, which means to measure. At first, 1 meter was defined as the 1/10,000th of the distance between the North Pole to the equator. Today, the definition of 1 meter is the distance that light travels in a vacuum in 1/299,792,458 seconds. Meter is widely used in sports, where many of track and field events like 100 meters, 200 meters, 400 meters sprints are all distance-based games. Why is the distance for marathon 42.195 kilometers? The story behind it is that a Greek soldier ran about 40 kilometers to bring the news of victory to Greece. The current distance for the marathon was adopted since the Fourth Olympics held in London. 42.195 kilometers is the distance between Windsor Castle to the Olympic Stadium. It was actually 42 kilometers, but Queen Alexandra, the wife of King Edward VII of the UK, asked to move the finish line to right in front of her seat. The Olympic Committee accepted her demand, which added another 195 meters from the original finish line, making the total distance exactly 42.195 kilometers. In addition to the unit of length, kilogram is another important unit for weight. 1 kilogram is the mass of 1 liter of water at the temperature of 4 degrees Celsius. However, because the density of water is unstable, the prototype corresponding to 1 kilogram of mass was redefined in 1889. As the international standard for mass, the cylinder-shaped mass prototype can bring confusion to the international community if stolen or destroyed. Therefore, it is stored in the deep basement located in the International Bureau of Weights and Measures in a protective triple glass, open to the public only once a year. As such, meter and kilogram are the common units used by the world as an international agreement. However, the U.S. still uses feet and yard instead of meter to measure a length and also uses ounce and pound as units of weight. Why? Liberia and Myanmar also don't follow the international system, too. For a long time, these countries have used other units, and do not want to cause confusion in the society and bear the enormous cost to suddenly change the units. They are reluctant to introduce new system of units. However, in May 2019, the definitions of 4 units will change, such as kilogram, a unit of weight, ampere, a unit of current, Kelvin, a unit of temperature, and mole, a unit of quantity of material. Is it really necessary to change the units that have been used well so far? The goal of the International System of Units, (SI), is to make unchangeable standards, but these 4 units are not stable. In other words, although these 4 units will not change, but over time, their standard amount has changed or became ambiguous. The representative example is the kilogram. According to the definition of International Kilogram Prototype, 1 kilogram was made of 90% of platinum and 10% of iridium. A lump of metal stored in the vault of the International Bureau of Weights and Measure was used as the international standard for 130 years. But, after a century, problems arose as the surface of the prototype was polluted and oxidized. In addition, in the process of cleaning it, about 50 microgram of minuscule change in the mass occurred, resulting in 0.00005 grams of error. This error affected the definition of mole, the unit defined based on the mass of carbon. From such change, the definition of ampere also became vague. Kelvin, the unit of temperature, was defined in a specific number as it is 1/273.16 of the thermodynamic temperature of the triple point in which gas, liquid, and solid exist simultaneously. The problem is the water. Although chemically, water has same gas, liquid, and solid, the temperature can change slightly depending on the ratio of an isotope, the mass of atoms making up water. As it became possible to define 1 kilogram with the error close to 0, the units related to mass needed to be modified. Ampere was redefined based on the default charge, E. Current is generated when electrons with electric charge move around. Therefore, it is essential to accurately measure the quantity of electric charge of 1 electron. Lastly, as mole, measuring the quantity of materials, became an independent unit as it is redefined based on Avogadro constant. The original definition was vulnerable to mass, but with the advance of technology, it now became possible to accurately measure the amount of atoms in materials. Definition of measurement units might change, but it will not make a significant impact immediately, as we do not need accurate measurement in our day-to-day lives. However, it will affect advanced industrial technology that requires accurate measurements. In particular, it is very important in the pharmaceutical industries, where new drugs are developed through increment changes to the amount of toxicity. South Korea was able to become one of the largest exporters of the semiconductors like DRAM memory and flash memory thanks to its advanced technology and precision measurements. Silicon boards, a standard of semiconductors, is a very thin film. South Korea is best at measuring nanometer, 1/1000th of a meter, thick films. The measurement means measuring the units of length, volume, and weight using rulers, bowls, and scales. There is a saying that how much a society knows about the concepts of quantity represents indices of civilization. Measurement and civilization have developed together. Concepts of quantity and primitive measurement started as humans began to farm and saved and traded agricultural products. As mentioned earlier, the first metrological model was based on human body parts. For example, length was measured using fingers or the palm of a hand, and volume was measured by how much you could hold in 2 hands, in one or two handfuls. Eventually, measurements were used to impose or pay taxes, and to measure the construction cost of buildings or large-scale civil engineering projects. As a result, community-based states began to form, with primitive economic and legal system. The measurement system played a critical role in the development of ancient Egypt's civil engineering and architecture, and as we can see on the murals from the time, it already had a very systematic structure. Likewise, the measurement system developed in different forms across different countries. For example, the Chinese units of measurement in China, the yard-pound system used in England and the US, and the metric system created by French scientists is still used today as the most representative system. Chen Shi Huang, who ended the Spring and Autumn period in unified China, realized the importance of units. He created and proclaimed the measurement system to be distributed, which included rulers, scales, and jialian, bowl used to measure the volume of grains in powder, as the standard for the units. He was able to unity different measuring system into one central system. A diversified measurement system gives too much room for abuse and exploitation. China's measurement technology is thought to have been first designed by the Huns in the 3rd to 4th century BCE, who settled around the Yellow River Basin. The measurement technology that started here later got spread to Korea and Japan. The various units used for measurement did not exist from the very beginning. Calculating size and volume and using measurements developed with the emergence of human civilizations and continue to evolve to be what it is today. An armful is the circumference a person can wrap with both arms. Long lengths that are hard to measure with our hands or arms can be measured using our footsteps, and depth can be measured using the height of a person. Of course, since everyone has different sized hands, lengths of arms, and strides, precise measurements may not be possible, but we can estimate the rough size and amount. Humans can use their hands more freely than other animals, which allowed us to create many different tools for measuring. For example, we can easily measure a length of something using a stick, and use stones to compare the weight of similarly sized objects. We can also use flexible vines to measure the circumference of round objects. As such, we can use our body and material in nature to measure an object. An object cannot be defined just by its mass or volume. It is also hard to say that two objects are the same just because their appearance and sizes are similar. For example, what would happen if we put a plastic bead and glass bead in the water? The plastic bead would float, but the glass bead would sink immediately. Density tells us whether an object will float or sink. An object with high density sinks while an object with low density floats. Between objects that are similar size, the one with higher density is heavier. Likewise, measurement is a useful tool to use to discover the secrets of nature. The ancient people already understood the concept of density, but they could not accurately measure it. Alternatively, they used wood, which has low density, to make boats to cross rivers and tied rocks on important objects so they would not float away. As societies developed and the number of people increased, using human body or objects in nature posed some limitations. For example, arguments can arise when two different unit systems are used in trade. Therefore, a universal measurement standard was needed. Of course, measurements are not just for tangible objects. Measurements also play an important role in determining the strength of natural phenomena such as the magnitude of earthquakes, intensity of typhoons, and amount of rain. The Richter scale, used to measure the magnitude of earthquakes, was developed by an American geologist named Richter. The Richter scale presents the amount of energy released during an earthquake. Magnitude 1 is similar to an explosive force of 480 grams, 1.05 pound, of explosives. Bigger number represents stronger earthquake. Earthquakes with a magnitude of 2 to 3 makes buildings sway a little and is rarely felt by humans, while inside of buildings shake on a magnitude of 4. Buildings shake a lot, inciting fear, at a magnitude of 5, while landslides occur with the land collapsing, thus roads and even cities getting destroyed with large-scale fatalities at over magnitude 7. Like earthquakes, typhoons cause a lot of damage. Hectopascal is used to measure the intensity of typhoons. Pascal is the international unit of pressure. Here hecto is a prefix meaning times 100. Wind, the flow of air, tends to blow from high to low pressure and get stronger as the pressure gets higher. The intensity of typhoons are measured based on the calculation that the Earth's standard atmospheric pressure is 1013.25 hPa. Which is more dangerous, a typhoon that has a central pressure of 970 hectopascal, or a typhoon that has a central pressure of 910 hectopascal? The wind is stronger when there is a bigger difference from the standard atmospheric pressure. Therefore, the typhoon with a central pressure of 910 hectopascal is more dangerous. Precipitation is measured using millimeters. Precipitation refers to the amount of rain that has fallen over a given period of time. When the weather forecast says there will be 5 millimeters of rain per hour, it means it will drizzle. You have to be outside in the rain for about 20 minutes for your clothes to get wet. 10 millimeters of rain per hour is a moderate amount of rain. There will be small puddles on the streets. 20 millimeters per hour would indicate stronger rainfall. Raindrops can be heard loudly, and water does not drain properly, causing water to collect that often causes damage. Rainfall over 30 millimeters per hour is torrential rain where caution is needed due to extensive damage caused by rain, such as from flooding. How are the different measurements utilized? The human body or tools from nature can be used to make estimates of a size and amount. However, in today's complex modern society, precise measurements are needed more than ever before. As a result, people began to modify natural material to make new measurement tools. For example, people use rulers to measure length. Straight rulers can be used to measure length or to draw multiple lines of the same length. By using a T-square, we can also easily draw parallel lines. Then people created and started using a tape measure instead of straight rulers, which are big and hard to carry around. Tape measures were handy as they can be rolled up, and even more flexible, which could be used to measure the length of curved objects, such as the circumference of a tree. As you very well know, a scale can measure an object's weight. A balance scale compares the weight of two different objects. When putting an item on the pan on each side of the balance scale, the heavier side will go down. A balance scale can be used to measure the weight of an object. Put the object you want to weigh on one side and a standard mass you know the weight of on the other. When the pans are level, the total sum of the standard masses equals the weight of the item. The scales we commonly use have a spring inside. The weight of an object is determined depending on how much the spring stretches or shrinks. Volume measures the amount of space occupied by a substance. Beakers or graduated cylinders are used to measure volume. They are similar to measuring cups in the kitchen. The cups have gradations to mark the volume. You can measure the volume of liquid, such as water and oil, with measuring cups, but other methods have to be used to measure the volume of solids. Let's take measuring the volume of a stone. When you put stones in a tank full of water, some of the water will spill over. This is because the stones are taking up a room, pushing the same amount of water out of the tank. The amount of water spilled has the same volume as the stones. This is the Archimedes Principle. It is also known as the principle of buoyancy. This principle allows us to make heavy iron ships float on water. Then what is buoyancy? Buoyancy is the force that allows an object to float in water or air. Buoyancy allows fish or heavy ships to float in the sea. Buoyancy is a force that allows objects to float by exerting a force upwards. The force is the same as the weight of water spilled over by the object. Therefore, buoyancy can easily be measured by putting an object in the water. The magnitude of buoyancy is the same as the weight of the water spilled over by an object. When you put a piece of wood in a cylinder filled with water, the water spills over. The weight of the spilled water will equal the weight of the piece of wood, indicating the weight and buoyancy of the piece of wood are the same. If the weight and buoyancy of an object are the same, it floats on water. The bigger the buoyancy, the better it floats. Then why do icebergs float? Large blocks of ice form due to snow not melting and are called glaciers. Glaciers do not melt but floats around the ocean. Such blocks of ice are known as an iceberg. Water, unlike other substances, water has a unique characteristic. Most substances' volume decreases when it goes from a liquid to a solid. However, when water goes from a liquid to solid, the volume increases. That is why when you put a glass bottle full of water in the freezer it cracks, the volume increases as the water goes from a liquid to a solid. Water molecules consist of one oxygen atom and two hydrogen atoms. When the temperature of the water drops, the irregularly moving water molecules are arranged regularly, forming solid ice. During this process, because of the characteristics of water molecules' structure, the molecules are arranged at regular intervals, causing the volume to increase. Density is mass divided by volume. If the mass is constant and the volume increases, the density decreases. Let us see why rafts float in water. Rafts float because the density of the wood making up the raft is less than the density of water. On the other hand, rocks have a higher density than water, so they sink when you put them in water. When the mass of ice and water is the same, ice has a larger volume, thus has a smaller density. That is why ice floats on water. What would happen if ice had a larger density than water, thus sink? What would happen to the fish in the lakes? The fish would have to flee from the ice whenever the water freezes up because at some point the ice on the surface of the lake would sink into the water. If the density of ice was larger than the density of water, icebergs in the ocean would sink too. Fortunately, the density of ice is less than the density of water, causing icebergs to float. If you put an iceberg in fresh water, 90% of it would sink while 10% of it will be above the water. Why does this happen? This is because the density of the ice is 10% smaller than the density of water. This can be explained using the buoyancy principle that Archimedes discovered while taking a bath. As mentioned earlier, the principle of buoyancy states that the volume of water that is the same as the volume of the object submerged generates a force that pushes the object upwards. Here, the magnitude of the buoyancy is equal to the weight of the water that has the same volume to the submerged object. For example, if the volume of the submerged object is 10 milliliters, the object gets a buoyancy of the weight of 10 milliliters of water. Since the density of water is 1 gram per milliliter, the mass of 10 milliliters of water is 10 grams. Now imagine what would happen if you put a 100-gram ice into this water. The volume of a 100-gram ice is around 110 milliliters. To make the 100-gram ice float, only 100 milliliters of the volume has to be submerged. Thus, a volume of a 100 milliliter of a 110 milliliters ice is submerged, while 10 milliliters is out.